Okay, this is example problem 5-116E from the back of the end of chapter problems in your book. So just to summarize the problem first, we have a 3 cubic foot rigid tank. It's initially filled with saturated water vapor at 300 Fahrenheit. Now a valve is opened. I'm going to indicate the valve here to you in blue. So there's our valve. Our valve is open, connecting our tank to a steam line where steam is flowing at 200 psia and 400 Fahrenheit. Now that steam at 200 psia and 400 Fahrenheit enters the tank until the tank is half full of liquid water, at which point the valve is closed. And we're told that heat transfer keeps the temperature of the tank at 300 Fahrenheit. So the first thing I'm going to do is I'm going to identify my system. So I've drawn my schematic here on the left, showing my tank and the valve and the steam line. So I'm going to identify my system first as being the contents of the tank. Okay, so I'm identifying that by this red dotted line. And I'm told that there's heat transfer from the tank that keeps the temperature at 300 Fahrenheit. So I'm going to write that, I'm going to add that in as Q. And then we also know that steam, which I'll draw in blue, we know that steam enters the tank when the valve is open. And what the question asks us is 3 things. I'm going to write these in green. A, we want to know what is the final pressure after the valve is closed. B, how much mass, what's the mass of steam that enters the tank? And C, what is the total heat that's been transferred from the tank during this process? Okay, so the first thing I'm going to do is I'm going to analyze this system, and I'm going to recognize that it is an open system, and it's undergone some process over delta T. And so I'm going to write my energy balance. For this system. Okay? So my energy balance, in a very general sense, is going to be the change in the energy of my control volume, which is the contents of the tank, and the change in energy, the change in energy of the control volume, or the contents of my tank, is going to be equal to the heat transfer, Q, minus the work done on or by the system, W, plus the mass in over the time delta T, M sub in, times the enthalpy of that mass, H sub in, minus the mass out during that time delta T times the H sub out. Now remember what we've talked about in class. The total energy of the mass in and out is actually theta, which equals H plus 1/2 V squared plus GZ. So inherent in this form of the first law that I've written, I've already made some assumptions. I'm assuming that my flow has negligible change in kinetic energy and potential energy in and out. I'm also going to make the assumption that no work is done on or by my system. And I assume that there's no mass out over this delta time. There's only mass in. Next thing I'm going to do is look at the change in energy of my control volume. And I'm going to recall that the change in energy of my control volume equals the change in the internal energy plus the change in kinetic energy of my system. Let's be consistent with our subscript. I can write control volume or system plus the change in potential energy of my control volume. Now, the next assumptions I'm going to make are that negligible change in kinetic energy in my system, negligible change in potential energy in my system. Again, that's the contents of the tank. And so, when I simplify all this down, and again, for the sake of space, I'm just explaining to you what my assumptions are, but always remember that you should write these out. You should make a list as you're writing out your problem. So for completeness, just remember to write out this list of assumptions that I'm discussing. Okay, so now all that's left on the left-hand side of my equation is this change in internal energy of my control volume, which I'm going to break apart even more and write this as the mass of my control volume, and I'm going to write this sub F for final, times the specific internal energy of my control volume, again, sub F for final, minus the mass of my control volume initially, times the specific internal energy of my control volume initially. And that's going to equal what's left on the right-hand side of the equation above. So all that's left there is heat transfer plus the mass of the steam that comes in times the enthalpy of that steam that comes in. Okay, so now what I'm going to do, and again, recall that I'm making assumptions along the way, and for completeness, you should always be listing those assumptions. Okay, so now I'm at the point where I have this form of my first law to describe my system for my system or control volume. Okay? So now I'm going to look at this and I'm going to say, okay, what do I know? What do I not know? Well, right away it pops out to me that if I go back and look at what the problem is asking, it's asking me, what's my final pressure? It's also asking me, what's the heat transfer? That's part C, Q. And what is the mass in? Okay, so there are two things in my energy balance that I'm looking for. So now what I should do is I should start thinking, okay, what do I already know? What can I find? So I'm going to go down this list of terms in my first law, and I'm going to find the values for these that I can. So what I ask myself is, what do we know? Okay, so I'm just going to start from the left and head to the right. So the first thing I know is I know my initial condition in the tank. So I could find from the tables, I know I have a saturated vapor, so I can find the initial specific internal energy of what's already in the tank, which is going to be the specific internal energy of saturated vapor at 300 Fahrenheit, which, recall, is what our problem told us the initial temperature of the tank is. Okay, so I'm going to go to table A4E, since this is in English units, and I find that that is 1099.8 BTUs per pound mass. Okay, and again, I got that from A4E, and that is a saturated table. Okay, so I'm going to go back to my equation here, and I'm going to say I have found one guy. Okay. All right, next I'm going to find the specific volume of my tank at that initial condition, because what that's going to let me do is, along with the volume of the tank, it's going to let me find the initial mass. Okay, so again from the table, the specific volume of the control volume at the initial condition is going to be the specific volume of the saturated vapor at 300 Fahrenheit, which again I get from table A4E, and I get that to be 6.4663 cubic feet per pound mass. And now I can find my initial mass of the control volume. Oops. Okay. Oops. There we go. Okay, and I'm going to find that using the volume of the tank, which I know, and that specific volume of the steam that I just found. So that's going to be 3 cubic feet. Oops. That's the volume of the tank over the 6.4663 cubic feet per pound mass that I just found from my specific volume. And that tells me, when I calculate that I have 0.464 pound mass initially in my tank. Okay, so going back now to my energy balance, I now have two of my terms in there, or two of my unknowns. So I have one full term defined. Okay, let's go to the next page, and I'm going to keep going with this. I'm going to keep finding these terms. So the next thing I'm going to find is the enthalpy of my steam coming into my control volume. Now, I know that this is steam. Oops. At 200 psia. And 400 degrees Fahrenheit. So when I go to my steam tables, what I find, recall as we talked about, first go to the the saturated tables, and I find that Psat at 400 Fahrenheit is 247.3 psia. Now, my pressure is 200 psia. So, since my P is less than Psat, I know that I'm superheated. Okay, so now I'm going to go to my superheated table, and going back up to my my value for specific enthalpy. What I find from the table is that my specific enthalpy of my steam in the steam line is 1,210.9 BTUs per pound mass. Okay, so now going back to my energy balance, I have another one of my unknowns. Okay, so plugging through them. So I know, let's go ahead and find, okay, so at my final state, what I realize as I'm going through these tables is that at my final state, T equals 300 Fahrenheit, and I realize I have a saturated mix. So I'm going to use that as I go through to find my the rest of my properties that I'm looking for. But what I realize is that I already know the answer to part A of my problem. Okay, so I'm just going to block that because, again, as we go through and we're finding these properties, we realize, oh, we're at a saturated mix at 300 Fahrenheit. That means we're at the saturation pressure. Okay, so knowing that I am at this, knowing this final state that I'm at, I still need two things if you look back at the energy balance. One is I need the mass of my control volume at the final state. Okay, so let's find that one now. So what do I know about my final state? I know that at my final state, 1/2 of the tank volume is a saturated liquid. And that's going to be 1.5 cubic feet. And I know the other half of my tank is filled with saturated vapor. And that's also going to be 1.5 cubic feet, because I'm told that at the end, half of my tank is filled with liquid. Okay, so next what I'm going to do is I'm going to go to my saturation tables, and I'm going to find my specific volume of my saturated liquid at 300 Fahrenheit, my final temperature, and I find that that is 0.01745 cubic feet per pound mass. And I find that my specific volume for my saturated vapor is 6.4663 cubic feet per pound mass. Let me rewrite those units to be a little neater. A little bit. Okay, so now what I'm going to do is I'm going to use these specific volumes and the fact that I know how much volume of saturated liquid and saturated vapor I have to find what the mass is of my liquid and the mass is of my vapor in the tank at the final state. All right, so let's go to the next page and let's do that. So the mass of the control volume at the final state equals the volume of the tank that is liquid over the saturated liquid specific volume plus the volume of the tank that is vapor over the specific volume of the saturated vapor. Let's plug in those values because we have everything we need here. And remember, these are the values from the previous slide that we just got off of the saturated water tables. Those are the values in the denominator here. Okay, so if you'll excuse these very messy units. Okay, so we have in the numerators, we have the volume of the tank, that is the saturated liquid of the saturated vapor, and in the denominators, we have the specific volumes. And when we plug those in, what we find is that we have 86.2 pound mass at the final state. So now what we can do, remember part B of our question, we already know part A, which is our final pressure. Part B wants to know what's the mass of the steam that has entered the tank. So the mass of the control volume at the final state minus the mass of the control volume at the initial state equals the mass in. So that's going to be 86.2 pound mass minus 0.464 pound mass, and we find that the mass into the control volume, the steam that goes in over this delta time, is 85.7 pound mass. Okay, so now we just have maybe one more thing that we need to find for our energy balance in order to finally solve for what we're looking for in our part C, which is the heat transfer. So let's go to our next page. And the last thing we need is the specific internal energy of the control volume at the final state. Okay, so going back to those saturated tables, saturated water tables, we find that the internal energy of the saturated liquid at 300 Fahrenheit, is 269.51 BTU per pound mass. And the specific internal energy of the saturated vapor is 1,099.8 BTUs per pound mass. So we know we have a saturated mix. And we know that because we're told that there's liquid and vapor in the final state. So we need the quality. Okay. Okay, so that's what we need to find. So remember the definition. Quality is the mass of the vapor over the total mass. And now we know that. So the mass of the vapor is our 1.5 cubic feet over 6.4663 cubic feet per pound mass. We just calculated that to find the total mass of the tank. That's the vapor portion. And then we're going to divide that by the total mass at the end, which is 86.2 pound mass. And so what we get is a very small quality of 0.003. Okay, so now we're ready to find our specific internal energy of our control volume at the final state. Which is going to be 1 minus x times UF plus x UG. And notice that this is a slightly different form of this equation. Your book uses the UFG and the x form. That's just a rearranged form of what I've written here. I just find this very easy to remember because 1 minus x is the mass fraction of the vapor times the specific internal energy of the vapor plus the mass fraction of the, times the mass, okay, let's start that one over. This is, on the first term is 1 minus the quality, which is the mass fraction of the saturated liquid, times the specific internal energy of the saturated liquid, plus the quality, which is the mass fraction of the saturated vapor, times the specific internal energy of the saturated vapor. Okay, we know all these values. When we plug them in, 0.997 times 269.51. That's a point right there. And this is BTUs per pound mass. Remember, this value just came from here. Okay. Ran out of room here. Plus 0.003, which is our quality, times 1099.8 BTUs per pound mass. And again, that number came from there. Okay, so when we calculate that, we find the specific internal energy of our control volume at our final state is 272.08 BTUs per pound mass. All right, now we have everything we need. We're going to go ahead and plug into our energy balance. So I'm going to rewrite the energy balance just to remind you. So we have our mass of our control volume at our final state times the specific internal energy of our control volume at the final state minus the mass of the control volume at the initial state times the specific internal energy of the control volume at the initial state equals Q plus M that's come in, that's the steam that's come in, times its specific enthalpy. So we can rearrange this. So again, that subscript is control volume at the final state, U of the control volume at the final state, minus M of the control volume at the initial state, U of the control volume at the initial state, minus M in, that's the steam, times H in, that's the specific enthalpy of the steam. And when we plug all that in, what we get again, I've run out of room, so I'm just going to write it down here. Okay, and when I now just plugged in the values, all those values that we just found, and when I calculate that, I get negative 80,831 BTUs. And recall that this negative means heat lost from the system. So our hot steam comes in, we're having heat loss from the tank, and so we're able to maintain our temperature at 300 Fahrenheit. All right, I hope that you found this useful. Just a reminder to go through and follow along and make sure that you can find the same values from the table that I've found.